Student, again starting or continuing the last part of the hypothesis testing. Again, this might take a few long minutes. I'll try to go as simple as possible, and if you find any problem or difficulties to understand, please let me know. We'll try to have a discussion over Google Meet. So this is the last section of the hypothesis testing. So in this section we present complete procedures for testing a hypothesis. Previously we tried to understand what are the names and what are the values, p values, z values, critical values, confidence intervals, those things through some examples. Now we'll try to understand the complete procedure for testing hypothesis made about a population proportion. This section uses the components introduced in the previous section for the p-value method, the traditional method or use of confidence intervals. So for that, requirements for testing claims about a population proportion P, the sample observations are a simple random sample. So here the sample observations are a simple random sample. The conditions for a binomial distribution are satisfied. So that sample observation or random sample satisfy the conditions for binomial distribution. The conditions NP greater than or equal to 5 or NQ greater than or equal to 5 are satisfied. So the binomial distribution of sample proportions can be approximated by normal distribution with mu equal to NP or sigma equal to root over NPQ. So here N is the number of trials, probability P is by sample proportion X by N. So here that is why X by N is the probability P, sample proportion X is sample proportion, P population proportion used in the null hypothesis, Q equal to 1 minus P. So Q is equal to 1 minus P, 1 minus of population proportion or used in the null hypothesis. Here this P and this marker is the sample proportion and N is the number of trials. Try to remember this throughout this video. So that is what conditions for being in binomial distribution is that NP should be greater than or equal to 5 and NQ should be greater than or equal to 5. Means both sides there should be same amount of values. N into P means this is the N into P, N into P or N into Q. Q is this one. Test statistics for testing a claim about a proportion is this. This is Z value. This is sample proportion. This is population proportion. That is what it's saying. This is population proportion. This is sample proportion. So sample proportion minus population proportion divided by PQ and N root over PQ divided by N. This is a Z value. Use the same method as described in section 8.2 and figure 8.8 as previously in the previous video. Use the standard normal distribution. We need to use the standard normal distribution. Use the same method as described in section. So we'll take a example here. An article distributed by Associated Press included these results from a nationwide survey of 880 randomly selected drivers. So here 880 randomly selected driver, among them 56 admitted that they run red lights. The claim is that the majority of all Americans run red lights. Our claim is that majority of all Americans run red lights. That is P greater than 0.5. The sample data are here N equal to 880 and sample proportion is 0.56, but our population proportion should be greater than 0.5. So NP equal to multiply with 880 into sample proportion, so population proportion, that is 440, and NQ 880 into 0.5, that is population proportion, 440 greater than or equal to 5. Example, so that is same continues. Sample letter A P, that sample proportion is 0.56. We'll use the p value method. For that z equal to this, we'll put the sample proportion here 0.56 and population proportion or probability 0.5, and root over 0.5 into 0.5 divided by 80 is equal to 3.56. so here h naught is p equal to 0.5 because we can put the equal symbol in case of null hypothesis, but we cannot put the equal symbol in case of p greater than 0.5, and alpha is 0.05. So referring to the table A2, we see that for value z equal to 3.50 and higher, we use 0.99 for the cumulative area to the left of the test statistics. The p value is 1 minus 0.99 is 0.001. Since the p value is 0.001 is less than the significance level of 0.005, so due to these values 3.56, our point remains in the distribution function at the 0.9999. so that is the area for the cumulative area to the left of the test statistics, and that is why p value is 1 minus this. So p value is very less than the significance level, that is significance level is 0.05. that is why it resides beyond this significance level. We reject the null hypothesis. There is sufficient evidence to support the claim. So here you can see the value of p is here 0.001 because p sample proportion is 0.56, or we can say z equal to 3.56. that is a test statistics, and our actual p population proportion is 0.5, or you can say z equal to 0. So here that is what we calculate from these values is z equal to 3.56, which is way beyond this area. This is the right tail test because why? So the critical region is an area of 0.05. We are finding that p greater than 0.5. That is why this is right tail test, and we are finding the critical region is an area of 0.05, only 0.05. We find that z equal to 1.645 is the critical value of the critical region. So our 3.566 more than or greater than 1.645. Then also we can reject the null hypothesis. So there is sufficient evidence to support the claim also. So that is another way to look at it. Here z value coming is 3.56, and our critical region is an area of 0.05. That is right tail test. In that case, z equal to 1.645. For a one-tailed hypothesis test with significance level alpha, we will construct a confidence interval with a confidence level of 1 minus twice alpha. We construct a 90% confidence interval. So we obtain our p value. Our p value should be in between 0.533 less than p less than 0.588. We are 90% confidence that the true value of p is contained within the limits of 0.533 and 0.588. Thus we support the claim that p greater than 0.5. So we can support the claim that p is greater than 0.5 because here you can see 1 minus twice alpha is 0.05 into 2, that is almost 1. So that is why we can say almost 90% confidence interval. So 90% confidence interval means that we obtain 0.533 less than p less than 0.588, which is the 90% confidence interval. We are 95% confident that the true value of p is contained because 0.56 remains in that area, contained within the limits of 0.533 and 0.588. Thus we support the claim that p is greater than 0.5. When testing claims about a population proportion, traditional method and the p-value method are equivalent and will yield the same result since they use the same standard deviation based on the claimed proportion. However, the confidence interval uses an estimated standard deviation based upon a sample proportion. Consequently, it is possible that the traditional p-value methods may yield a different conclusion than the confidence interval method. So here again, obtaining the sample proportion, sometimes sample proportion sometimes is given directly. 10% of the observed sports cards are red. Then we can say that observed sports cards is 10%, means sample proportion is 0.10. And sometimes we need to calculate the sample proportion. 96 surveyed households have cable TV and 54 don't, is calculated using. So our total observed household is 96 plus 54, and observed is observed households which have cable TV is 96. So our sample proportion is 0.64. Again, another example, when Gregory Mendel conducted his famous hybridization experiments with peas, one such experiment resulted in offspring consisting of 428 peas with green pods and 152 peas with yellow pods. According to Mendel's theory, 1/4 of the offspring peas should have yellow pods. Use a 0.05 significance level with the p-value method to test the claim that proportion of peas with yellow pods is equal to 1/4. Now here we can say that total number of samples is n equal to 428 plus 152. Green is 428, yellow is 152. Y by t. Our sample proportion is 0.262. How? 152 divided by 580 is almost 0.262. And p equal to 0.25, that is 1/4. That is why it is saying that p-value method to test the claim that proportion of peas with yellow pods is equal to 1/4, that is 0.25. So our hypothesis is that null hypothesis is that p equal to 0.25, and alternative hypothesis is that p is not equal to 0.25. Our sample number of sample is 580 and our significance level is 0.05 is taken, and sample proportion is 0.262. So if we put those values here, we can find that z value as 0.67. Since that this is two-tailed test, because we are going in both side of the equal symbol of that null alternative hypothesis, that is why this is two-tailed test. The p-value is twice the area to the right of the test statistics using table A2. Z equal to 0.67 is 1 minus of 0.7486, that is twice of this. So twice of z value, 1 minus of twice of z value equal to 0.2514. Then z equal to 0.2514. Twice of 67 is almost so p-value is twice of this is 0.5028. So our actual p-value is taken as 0.25, but this is as this is a two-tailed test, we need to take the p-value as 0 twice into 0.2514. So 5028, and we fail to reject the null hypothesis because that is not inside that 0.67 level. There is no sufficient evidence to warrant rejection of the claim that 1/4 of the peas have yellow pods. Another example, we have a sample of 106 body temperatures having a mean of 98.20 Fahrenheit. Assuming that the sample is a simple random sample and that the population standard deviation sigma is known as 0.62, use a 0.5 significance level to test the common belief that the mean body temperature of healthy adult is equal to 98.6 degree. Use the p-value method. So here, given the sigma, that is standard deviation, when it is known, then we can use this equation. So using this equation, we find that z value, where x mean is that 98.2 of this observed sample, and 98.6 is that population sample or population proportion or population value, that is mu of x, mean of x, or whatever mean of sample we have getting, that is 98.2 minus 98.6, divided by 0.62, that is standard deviation, and divided by number of samples 106 equal to minus 6.64, and that is coming negative. So our null hypothesis is that mean healthy adults having equal to 98.6, and our alternative hypothesis is that this is not equal to 98.6, and that is why if as this is not equal to symbol, then we can say that this is two-tail test. That is why alpha equal to 0.05 and x mean equal to 98.2 of the sample mean, and sigma is the sample standard deviation 0.62. This is a two-tail test, and test statistic is to the left of the center. Test statistics is left of the center because this is negative, and so the p-value is twice the area to the left of z equal to 0 minus 6.64. We refer to the table A2 to find the area to the left of z equal to minus 6.64 is 0.001, which is and as this is two-tail test, we need to multiply this with 2, then p-value is become 0.002, 0.002. So sample that is same thing is here, that is mu equal to 98.6, that is z equal to 0. Because test is two-tail test, the p-value is twice the red shaded area. Area is 0.001. Sample data is x mean, that is 98.20, or z equal to 6.64. Because the p-value is 0.002 is less than the significance level alpha equal to 0.05. That is why we can reject the null hypothesis. There is sufficient evidence to conclude that the mean body temperature of healthy adults differs from 98.6. We now find critical values of values to be z equal to 1.96 and z equal to 1.96. We would reject the null hypothesis since the test statistics of z equal to minus 6.64 would fall in the critical region. So obviously that value will be fall in the critical region. Also this is the limit, or this is the critical value, whether it is positive 1.6, whether it is negative 1.6. So that is why we can reject the null hypothesis. There is sufficient evidence to conclude that the mean body temperature of healthy adults differs from 98.6. For a two-tail test with a 0.05 significance levels, we construct 95% confidence interval. Use the methods of section 7.2 to construct 95% confidence interval, because 98.08 less than mu, that is confidence intervals less than 98.32. So if mu remains in that region, then only we can say that that thing will be claimable. We have 95% confidence that limit 98.08 and 98.32 contains the true value of mu. So it appears that 98.6 cannot be true value of mu. That is the point. If the value remains in that region, then only we can say that mu is true. Otherwise, we cannot say that 98.6 cannot be a true value of mu. If under a given assumption there is extremely small probability of getting sample results at least as extreme as results that are obtained, we conclude that the assumption is probably not correct. When testing a claim, we make an assumption of equality. We then compare the assumption and sample results, and we form one of the following conclusions. If the sample results can easily occur when the assumption is true, we attribute the relatively small discrepancy between the assumption and the sample results to chance. If the sample results cannot easily occur when that assumption is true, we explain the relatively large discrepancy between the assumption and the sample results by concluding that The assumption is not true, so we reject the assumption. That means we reject the null hypothesis. Again, another section, that is when we don't know the mean. This section presents methods for testing a claim about the population mean when we don't know about the value of mean, or sorry, not mean, that is sigma. The methods of this section use the student t distribution introduced earlier. The sample is a simple random sample. The value of the population standard deviation sigma is not known. Either or both of these conditions is satisfied, the population is normally distributed or n greater than 13. So then we will use this equation in case of sigma is not known. P-value and critical values found in A3, degrees of freedom n-1. So I'll try to go through this example. Here dataset of 13 in appendix B of the text. So this is actually, you might not understand this because this is referencing to another context or text. So we'll try to avoid this. So anyhow, we try to follow various methods to testing a hypothesis, and also try to understand the basics terminologies, and obviously you will face some problem while claiming the test because something might not be understandable, but try to at least try to execute or try to do this exercise at least once to test any hypothesis. Then only you can understand the procedure. And if you have any doubt, or if you want to understand anything regarding this hypothesis testing, please let me know. We'll try to resolve the issue over Google Meet. So that's it today in this video. We'll try to go for new topic in incoming videos. Thank you.